In 2026, the Republic of Kenya initiated a hardline industrial policy, a definitive blanket ban on all raw mineral exports. For decades, the standard economic model relied on extracting African raw earth, like titanium, and shipping it across oceans to foreign refineries. This framework left the host nation with degraded land and negligible financial return. This dynamic fuels the classic resource curse, an economic paradox where massive natural wealth correlates directly with domestic stagnation and poverty. The Kenyan government's rationale to break this cycle is strictly structural. As President William Ruto noted, the country possesses the raw material, the domestic market demand, the institutional capital, and the industrial capacity to refine these resources at home. The strategy intends to force a transition from acting as a passive peripheral node in the global supply chain to operating as a sovereign processor of advanced materials. At the apex of this strategy is the domestic refinement of high-purity niobium, a critical transition metal required to engineer next-generation quantum computing architectures. Kenya's export ban functions as a geopolitical pivot, engineering a zero-carbon, sovereign supply chain for the quantum era. The financial engine of the 2026 mining regulations relies on a severe restructuring of the state's mineral royalty sharing formula. This flowchart outlines the new tripartite structure. Revenue from domestic beneficiation is divided 70% to national, 20% to county, and 10% directly to local host communities. This funds targeted adaptation projects, specifically drought-resistant agriculture and resilient water infrastructure. In practice, this finances hard infrastructure. Vulnerable agricultural zones facing severe climatic shocks receive capital for assets like solar-powered irrigation pumps, stabilizing food production. Linking industrial extraction directly to agricultural survival solves a critical operational friction. It secures necessary local community buy-in for the construction of heavy industrial refineries. Domestic mineral beneficiation effectively becomes a decentralized financial engine, converting raw earth into grassroots climate resilience against increasing ecological shocks. This aggressive downstreaming policy closely mirrors Indonesia's 2014 and 2020 bans on raw nickel exports, which successfully forced foreign companies to construct domestic smelters. However, the Indonesian model suffers from a severe structural flaw. To meet the massive energy demands of rapid industrialization, the country powered its new smelters with captive, off-grid coal plants, generating immense greenhouse gas liabilities. Refining critical minerals with fossil fuels destroys their value in Western markets, which increasingly enforce strict carbon border adjustment mechanisms that penalize high-emission imports. Kenya possesses a geographical countermeasure, the East African Rift System. This geological fault line provides thousands of megawatts of continuous, carbon-free baseload geothermal power. To leverage this, the state is co-locating special economic zones directly atop geothermal hubs, like the Olkaria field. This bypasses expensive national grid transmission costs, routing power straight to heavy industry. This diagram illustrates the cascading industrial economy at Olkaria. Primary consumers, like refineries, draw high enthalpy steam. Lower enthalpy heat cascades to secondary processes, like fertilizer production. Finally, residual heat is used for agricultural drying before cooled water is re-injected, creating a closed-loop system. By embedding heavy refineries directly into these geothermal zones, Kenya produces refined materials with a near-zero carbon footprint, perfectly aligning with the strict Scope 3 emission targets of global manufacturers. The operational capacity of Olkaria is specifically calibrated for targets like Mrima Hill, a coastal deposit holding an estimated $62.4 billion in unexploited value. Geological mapping of the site confirms massive concentrations of highly strategic elements, primarily niobium, alongside a suite of vital rare earth metals. Extracting these metals presents a severe geological hazard. At Mrima Hill, these coveted elements are physically bonded within the host rock, alongside highly radioactive thorium. The standard metallurgical process for isolating rare earths relies on aggressive chemical leaching. This method strips the host rock, but generates massive volumes of toxic wastewater filled with radioactive isotopes. Decades of unregulated rare earth processing in Baotou, China, offer a grim precedent. Unchecked extraction created sprawling, toxic tailings lakes that decimated the local ecology. To prevent an ecological collapse on the Kenyan coast, the National Nuclear Regulatory Authority requires strict oversight. The winning extraction consortium must deploy advanced closed-loop technologies designed to safely vitrify and encapsulate all radioactive tailings. Without uncompromising engineering safeguards to manage the thorium byproducts, the beneficiation blueprint will trigger an irreversible socio-political and environmental disaster. If the state successfully navigates the geophysics and the regulations, the technological endpoint is securing the global supply of high-purity niobium for quantum computing hardware. In the architecture of quantum processors, information is held in superconducting circuits known as qubits. While historically built with aluminum, niobium operates at higher temperatures and tolerates a vastly wider magnetic field, offering superior computational capacity. This diagram illustrates the critical engineering bottleneck for niobium. On the left, the lossy oxide problem. Pure niobium rapidly oxidizes, destroying quantum information through decoherence. On the right, the solution. Applying ultra-thin capping layers like tantalum during fabrication prevents the destructive oxide from forming. This exact encapsulation technique successfully extends median qubit lifetimes well above 300 microseconds, unlocking massive new computational potential for complex problem-solving. Kenya is integrating this supply chain directly into local research at Konza Technopolis, a massive digital hub where Pan-African institutes collaborate on quantum material fabrication. By piping clean niobium from the Olkaria refineries straight into the research labs at Konza, the nation transitions from a raw earth exporter into an indispensable node in the future of computing. The intersection of global capital, geopolitical tension, and advanced physics makes the success of Kenya's beneficiation highly volatile and uncertain. This matrix outlines two diverging trajectories. Regulatory failure leads to the worst-case scenario, polluting fossil fuels and toxic ecological disaster. Conversely, rigorous enforcement achieves the best-case scenario. Geothermal integration and strict safeguards allow Kenyan niobium to command a green premium. The physical drivers behind these policies remain. The historical model of shipping raw, unrefined African earth across oceans is ending. The Kenyan strategy suggests that economic sovereignty requires a synthesis of natural geophysics and uncompromising industrial policy to build the technological foundations of tomorrow.